The operation of protection schemes, and indeed the detection of fault conditions, depend very much upon the characteristics of the fault itself. Certainly, the nature of the fault is the principal factor in determining
1. Magnitude of fault current, 2. Change in magnitude of voltages, and 3. Change in phase angle relationships.
In this videotape, we should be looking at the different types of faults and their effects.
In this simple one-line diagram, we have a generator feeding power through its circuit breaker and transmission line. The load is 300 amps at a phase to neutral voltage of 21 kV. For simplicity, let us draw this out as a single-phase circuit. This 1.5 ohm impedance here represents that of the generator, while the 0.75 ohms here represents the impedance of the transmission line. As this is single phase, we can calculate the impedance of the load simply by dividing 21 kV by 300 amps. This comes to 70 ohms. Observe that the load impedance is far greater than the generator and line impedance. The return line also has the impedance of 0.75 ohms, and the current, 300 amps, circulates continuously in this closed single-phase circuit. Now let's see what happens when we add further load. Let's say this is also of 70 ohms, and of course it will be in parallel. Our total load now is 600 amps. Note that when we added load, we effectively reduced the load impedance. In this case, the equivalent impedance of these two loads is equal to 35 ohms. As extra load is added, the voltage at the generator must be increased slightly in order to maintain 21 kV at the load. Let's work out the voltage drop between the load and the source. This is simple. Total impedance comes to 3 ohms. Multiplying this by 600 amps gives us a voltage drop of 1800 volts, that is 1.8 kV. So the internal voltage at the generator is 22.8 kV. Now let's see what happens if we have a direct short circuit at the far end of the line right across the load. The load impedance now falls to 0. As a result, the total current circulating through this circuit will now be 22.8 kV divided by 3 ohms, which equals 7,600 amps. This is a tremendous change in magnitude of current, increasing from 600 to 7,600 amps. And what about the voltage throughout the system? Well, as we consider the short circuit to contain no impedance at all, the voltage across the load will now be 0. And at this point, at the beginning of the line, voltage will be 22.8 kV, the internal generator voltage, minus the voltage drop across the generator impedance. That is 22.8 kV minus 7,600 amps times 1.5 ohms equals 11.4 kV.
We know in practice that it is all a lot more complicated than this. We have 3 phases to worry about, and moreover, the impedances may be at different angles and therefore would have to be added vectorially. But the conclusions are very clear.
First, note that an increase in load decreases the load impedance, and therefore decreases the total circuit impedance. Secondly, as a result of the short circuit, the total impedance is greatly reduced, and the consequent increase in current circulating in the system is dramatic. In our example, it has increased by approximately 13 times. Thirdly, the voltage at the short circuit has decreased to 0, or at least to a very low value. As a result, the voltage all along the line is also reduced. When studying fault conditions, we always consider that the internal voltage of the generator remains constant. This is based on the assumption that the time interval will be extremely short before protection equipment clears the fault. In practice, it is probable that the generator automatic controls may attempt to increase generator internal voltage in order to compensate for some of the voltage drop downstream. However, this would take some seconds and therefore should not interfere with the operation of protection relays, nor with our studies of fault characteristics.
Let's take our study a step further now and consider the magnitude and phase angle of the various impedances.
Here is another single line diagram, but this time of a more complicated system. The impedances line to neutral are represented here. The generator, the step-up transformer, the transmission line, the step-down power transformer, and here the total distribution circuit, including the distribution transformer, and eventually the impedance of the load. Now, let us plot on a resistance-reactance diagram impedance as seen by a relay located after the generator step-up transformer. First, we have here the impedance of the generator. This is quite a low value and also consists mainly of reactance, as can be seen from the large phase angle. Similarly, the step-up transformer impedance is composed almost entirely of reactance, and is therefore close to 90 degrees. The impedance of the transmission line is plotted here at about 60 degrees. The impedance of the step-down transformer is shown at almost 90 degrees. And here is the combined impedance of the distribution line and distribution transformer. Note that the impedance of the distribution system is at a lower phase angle at about 40 degrees. And here we add the impedance of the load, which is of much higher magnitude and also at a much lower phase angle. The power factor of the load is generally in the order of 0.9 to 0.95. The corresponding angle to a cosine of 0.9 is about 25 degrees. The total impedance of the circuit is shown by this line. If we have a short circuit close to the load, you can see that there will be a dramatic decrease in impedance, but its phase angle will increase considerably. As the fault becomes closer to the source, the impedance is much less. Consequently, the fault current will be much higher. It is important to remember that the generator itself contains impedance. This serves to limit the magnitude of fault current, even for a short circuit on the generator terminals. Of course, the short must be cleared quickly to avoid serious damage.
Now, these examples that we have been looking at are very simplistic because we are not considering the three-phase system.
Here we show a similar simple power system, but this time all three phases are included. The generator is Y-connected, and its neutral is grounded. If the load is balanced, the phasor diagram will look like this. I'm sure you'll remember this from earlier study of electrical fundamentals. The voltages and currents are of equal magnitude and phase displacement. However, a fault occurring on this system will cause considerable imbalance.
Let's consider just what types of faults can occur. The most common are
three-phase, three-phase to ground, phase to phase to ground, single phase to ground. With the three-phase fault, all three phases, A, B, and C, will be effectively connected together at the fault location, and a very heavy current will flow through the conductors, but the system will still be balanced. where all three phases are grounded by a fault, this is considered to be the same as a short circuit across all three phases. The voltage at the fault is reduced close to zero on all three phases, and it remains balanced. The second type of fault is the phase-to-phase, where there is a short circuit between two conductors only. In this case, if, say, phases B and C are connected together, then heavy fault current circulates in phases B and C only. Phase A can continue to provide its load. Another type of fault is the phase-to-phase to ground. Fault current flows in the shorted phases and also to ground. 95% of faults on the power system are single phase to ground. Here the load will continue to be supplied by all three phases, but there will be a heavy flow of current to ground from the faulted phase. This will circulate back and return up the solidly grounded neutral to the generator.
Now, before we go on to study the effects of these faults in more detail, let's take a break. Please switch off the tape now and go through this material in your work.